Hello, welcome to this video. In this video we are going to enter into protected mode. It will give us a 32-bit address space, the ability to use a maximum of 4 GB of addressable memory, and it enables the system to enforce strict memory and hardware protection. And we also have access levels, also known as rings. So, what do we need to do to enter into protected mode? First of all, we need to disable interrupts. In protected mode, most interrupts are disabled. We cannot use them. Then we need to enable the A20 line. Basically, it allows us to access memory more than the 1 MB limit that we have in real mode. And then we have the global descriptor table. The global descriptor table includes information about segments. In protected mode, memory is divided into segments. Each segment can hold code, data, or stack information. Each segment is defined by a descriptor in the global descriptor table. So, the global descriptor table is basically a data structure that contains descriptors. Basically, the descriptors contain information about each segment of memory. So, how do we set the global descriptor table? How do we define it? We have, first of all, the GDT null. It is a mandatory entry. It has to be first, and it's just a placeholder. It's not used, but it has to be there. Then we have the GDT code. The GDT code, it describes the code segment. It is the code segment descriptor that defines the code segment. And it has the lower 16 bits of the limit, FFFF. These, along with these high 4 bits, give us a limit of FFFFF. And because the granularity flag is set here, this one basically, this limit is in 4 kilobyte blocks. Not byte blocks, but 4 kilobyte blocks. Which means that with this math, you will see that the limit for this segment is 4 gigabytes. And then we have the 9A access byte. This is in binary. This is in hexadecimal. So, we have the present bit, allows an entry to refer to a valid segment. We have the descriptor privilege level field. 0 is the highest. We have the descriptor type bit. If it's set, it defines a code or a data segment. This is a code segment. We have the executable bit. This means that it is a code segment which code can be executed from. We have the conforming bit. If it's 0, code in this segment can only be executed from the ring set in the descriptor privilege level, and the 0 is the highest, as we said. And we have the readable bit. Read access for this segment is allowed. And we have the access bit. The CPU will set it when it accesses this segment. We can set it in advance, of course, but we will not. Then we have these 4 flags here. We spoke for the granularity flag, and then this one, the next one, defines that it is a protected mode segment, a 32-bit segment. The other 2 are zeros because we are not in log mode and because this one is reserved. Then we have the data segment. The data segment is very similar but with some key differences. The limit is the same, but the access byte is different, is hexadecimal 92, this one in binary. The present bit is the same, the privilege level is the same, and this one is the same too, but the executable bit is 0 because it contains data, not code. And the direction bit shows that this segment grows upwards. Then we have the readable writable bit. It's 1, so write access is allowed. Read access is always allowed for data segments. And then we have the access bit. The CPU will set it as before when it accesses this segment. And the same 4 flags here exactly as before. And then we define the GDT end to know the end of our data structure. Here we define the GDT descriptor. It contains the size of the GDT and the address of the GDT. To calculate the size, the only thing we have to do is subtract the start address from the end address and then subtract 1. And the address is the label that we saw at the beginning of the global descriptor table. So, now, I have created this label here called enter protected. I use it here when someone enters P. Basically, we enter into protected mode. We go to this label here. So, what does this label do? First of all, we clear all interrupts. And we set the registers as we did before here to have a clean state. And after we do it, we set interrupts back. Then we clear all interrupts again. We load the GDT descriptor with the LGDT instruction. And we set the protection enable bit in the control register 0. And then we do a far jump to this address, to the code segment with offset load 32. The code segment is basically 08 hexadecimal. Why? Because its entry in the global descriptor table is 8 bits in size. So 0, 8, 10, these are hexadecimal numbers. Basically, this is decimal 16. So we jump to this, and with the offset of load 32. In load 32, it's just a label. It is the code that we start in protected mode now. And we have the use 32 to show that we are writing a 32-bit code now. The first thing we need to do is load our kernel into memory. In order to load our kernel into memory, we need to read from disk. In protected mode, we cannot read from disk the same way like we did before. Why? Because in protected mode, we don't have access to BIOS interrupts, as we said before. In the past, we used interrupt hexadecimal 13 to read from disk. But now we have to do something else. We have to use the advanced technology attachment interface in the LBA mode. So, in EAX, we put the start address, the sector that we want to start reading from. This will be sector number 6. Why? Because we have 5 sectors with the boot sector and the second stage boot sector. So we start reading from sector 6. Then we set here the number of sectors that we want to read. I have set it to 100. I will show you the make file and you will understand why. And we say that we want to load the kernel to 1 megabyte of address. It is a very common place to load the kernel, in 1 megabyte. So here I have a routine set to print something in protected mode. We will not use it now. I had it for testing. I will leave it here in case we need it in the future. So what does this code do? The LBA is a method of specifying the location of blocks of data stored on hard disk. So we're going to use this. And the ATA is a standard interface for connecting storage devices such as hard drives and CD-ROMs drives to a computer. So, let's do it. First of all, we push all general purpose registers to save our state. And then we send 0xE0 hexadecimal for the master. We don't use a slave drive, we have a master drive. And we OR it with the highest 4 bits of the LBA to port 0x1F6. So basically it's this code here. Then we send the sector count, the 100 that we saw before, to port 0x1F2. Then we send the low 8 bits of the LBA to port 0x1F3. And then the next 8 bits of the LBA to port 0x1F4, and then the next 8 bits of the LBA to port 0x1F5. And then we send the read sectors command 0x20 to port 0x1F7. And then we push ECX, and then we check if the disk is ready to transfer data. And how we do that? By reading from port 0x1F7 and testing for bit 3. So, if everything goes right, we transfer 256 16-bit values, an unsigned 16-bit integer at the time, into our buffer from port 0x1F0. So, we do that and we read and we put our kernel into memory, and then we jump to it. What is our kernel? I have written a little bit of code, it's almost nothing, but we specify here that it's going to be of ELF format. With the NASM assembler, you can do that by setting a compiler flag, an assembler flag. When you assemble, you just put a flag there. But with fasm, you have to put it at the start of the file. We say that we're writing a 32-bit code, and because we started using C in our kernel, here I'm calling the kernel main from our C code. I'm not calling it, I'm making it available to call later. And I set the start label as public. So, what I said before about the code segment and the data segment, their offsets. And we have the text section. The text section contains code that will be executed. So, we set up the segment registers. We set the DS, the ES, the FS, the GS, and the SS, and they point to the data segment. Why? Because we want them to reference the correct memory locations defined in the global descriptor table entry. And where are these data, like global variables and stacking operations? In the data segment. And then we have the EBP register, also known as the base pointer or frame pointer. It is used in x86 architecture to manage stack frames for function calls. A 2 megabyte address is a good address that we can use. It's a free area. And then, as we said, we enable the A20 line. I have set here the link from OSDev if you want to read more. Basically, we read the current value from port 0x92. We set the second bit to enable the A20 line, and then we write the new value back to 0x92 port. And we call our kernel main from C. So, our C code is quite simple. For now, I just for testing, I copied pasted this code from the OSDev bare bones tutorial, just to know that it works. But how can we write in C? How does it work? Let's check a few things for that. Let's check our linker. The linker defines how the various sections of an executable are arranged in memory when creating a binary output. So, we have the entry. Let me open the kernel file here so you can read. So, we have the entry as start, this one that we defined as public, and this is the entry symbol of our program. We say that we want to load our kernel to 1 megabyte. This means the subsequent sections will be placed starting at 1 megabyte of memory, because the first megabyte is reserved usually for real mode, like BIOS interrupts. And then we define how every section of the executable will be. We have the text section that will be our executable code, aligned to 4 kilobytes. Then we have the read-only data, like constants and string literals. Then we have the data section that contains initialized data. We have the BSS section, which contains uninitialized data, variables that are declared but are not initialized. And the common this one, includes all common symbols which are uninitialized data that can be defined in multiple places. And we have an ASM section for assembly code. This is our linker file that will link everything together. And then we have our make file. We have a few changes in our make file. Let's start from the bottom. We have our kernel.o and we build it by using kernel.c. We are using a cross compiler for that. Why? Let's see. A cross compiler is a compiler that's independent of an operating system. There are no libraries like the standard library. There are no functions like alloc or realloc. These functions depend on the operating system. We don't have an operating system. So we have to build a cross compiler. For the ones that use a Debian-based distribution, you have to follow these instructions. For other distros, you can follow those instructions here. If you have an Arch-based distribution, you can use an AUR package. It will be very easy to install. So if you have Arch, Manjaro, or something else based on Arch, you can use an AUR package for this. But if you don't, you have to follow the instructions here to build a cross compiler to be able to use C in our code. So we use the elf GCC with the flags that we defined here, pretty standard for OS development, and we create the build kernel.o. We put it here in the files. We just use fasm to create the kernel.asm.o, this one, and then we create the kernel.bin. And after we create the kernel.bin, we put it in our final binary, the os.bin. And at the end of the binary, we add 100 sectors of 512 bytes each. That's why we read 100 sectors with the LBA. So, how do we create our kernel.bin file? Basically, we create a final kernel file which is relocatable. Basically, our linker will change it. It will relocate the things that it has inside. And we use GCC. We create the final kernel by using these object files here. And then we link everything together using the GCC with these flags, with the linker that I showed you before, and we create the kernel bin. And we put the kernel bin in the final binary. So, let's see. We use kemu with a different command now, hard drive command. We press and we see the option to enter into protected mode. We press it and we have entered into protected mode. It is the same message that we have here. So this is how we enter into protected mode. I know it was a little bit challenging. If you have questions, please write them in the comments and I will be very glad to answer them to the best of my ability. I will post links for everything from the OSDev website. It is an amazing resource. If you like this video, like and subscribe, and I'm looking forward to the next one. Thank you very much for being here.